Hello everyone, welcome to this session on hydraulic turbines. So in last session we have already seen the working and construction of different hydraulic turbines. Today we will solve some of the problems. Mainly we will concentrate on the three types of turbines, that is Pelton turbine, Francis turbine and Kaplan turbine. So first we will look into Pelton turbine. This is a figure showing the various parts of a Pelton turbine. So recall that Pelton turbine is a tangential flow impulse turbine. It is mainly used for high heads. So coming to the important points to be remembered for Pelton turbine, we have discussed all this in detail in our last session. So we'll just go through this. These all relations are important for solving the problems. Now we will solve one problem. A Pelton wheel has mean bucket speed of 10 meter per second with a jet of water flowing at the rate of 700 liters per second under a head of 30 meters. The buckets deflect the jet through angle 160 degree. Calculate the power given by the water to the runner and the hydraulic efficiency of the turbine. Coefficient of velocity is 0.98. So first we will list out the given things. Here the bucket speed, which we will denote it by a u, that is in the case of Pelton wheel, u1 is equal to u2, that is speed of the bucket is 10 meter per second, and discharge is given 700 liters per second, which is 0.7 meter cube per second. Head of the water, that is capital H, is 30 meters, and the angle of deflection is 160 degree. If it is given the angle of deflection is 160 degree, we can find out phi, that is it will be 180 minus 160 degree, that is 20 degree, and coefficient of velocity cv is equal to 0.98. So from the equation we already know that v1 is equal to cv into root 2 gh. From that we will get the value of v1, and vr1. Before solving vr1 we have to see this velocity triangle. So this is the velocity triangle of a Pelton wheel. You can see that the inlet, at the inlet side, it will be more or less a straight line with all the quantities marked like this. This is u1, this is vr1, vw1 which is equal to v1 which is equal to vw1, which is the world velocity. And at the outlet we will have all these quantities. We have already seen how to draw this velocity triangle in our last session, so I am not going to explain in detail about this. All the quantities will remain the same, that is this will be v2, vr2, all this will be same, only the values will be changing as per the question. So here again, to find vr1 we can see that vr1, as it is 1, it will be in inlet side, and 2 denotes the outlet side. So vr1, this length, we can see that it is v1 minus u1. You can see from the velocity triangle. So to solve this problem we have to draw this velocity triangle, then only we can find out the associated values. So v1 we already have got 23.77, and u1 is 10 meter per second. So from that we'll get the value of vr1, and vw1, which is same as v1, so it is same 23.77 meter per second. Now we are asked to find out the power and the hydraulic efficiency. So we have to find out the force exerted and then find out the power. And again, to find out we have to find out vr2. So we will look into the outlet velocity triangle, that is this part. This is the outlet velocity triangle. So in that vr2 will be same as vr1. So why? Because we are assuming that there is no loss due to deflection. So the velocity with which the water is striking will be same as the velocity with which it is exiting. So we can write vr2 is equal to vr1 by neglecting the losses. Now vw2, from the figure we can see that vw2 is equal to vr2 cos phi minus u2, That is, you have to take this bigger triangle. In that, cos phi is nothing but uh, uh, is V cos phi is U2 plus VW2 by VR2. So from that VW2 you can write like this. VW2 is VR2 cos phi minus U2. All these relations you get from the velocity triangles. Okay. So VR2 we already know, cos phi also we know. Substituting the values we will get VW2 value. Again we have the work done equation. This equation we already know is rho a v1 into vw1 plus vw2 into u. You have seen all this equation from the impact of jet portion. Substituting the values for finding out the value of v1 vw2 only, we have solved and find out the values of vw1 and vw2 from the velocity triangle, and finally writing the relation for work done per second and substituting the value, we will get a work done as 1,86,970 Newton meter per second. So power usually expressed in kilowatts. So dividing it by 1000, we'll get 186.97 kilowatt. And again, hydraulic efficiency. This again we have an equation for hydraulic efficiency. So substituting that value, we will get the efficiency as 94.54%. Now we will look into another problem. This is different from the problem that we just solved. We will read the problem and find out how it is being solved. A Pelton wheel is designed for the following specification. Shaft power is given, head is given, speed is given, overall efficiency, and the jet diameter is not to exceed 1/6 of the wheel diameter. You are asked to find out wheel diameter, the number of jet required diameter of the jet, and you are given KV1 and KU1. So we will see what is this KV1 and KU1. So the specialty of this problem is that here we have to solve this without drawing the velocity triangle. The velocity triangle will not give you much value data here. So this is a problem of rather a design problem, designing of a Pelton wheel. So again, writing the given things, you are given the shaft power, which is shown as SP. Head is given 380 meters. Speed is given. Speed usually we denote by capital N, 750 RPM, and overall efficiency eta O, 86%. And you are given the jet ratio to wheel diameter. So the jet diameter to wheel diameter. So jet dia is small d and wheel dia is capital D. So that is given by 1/6. And then what is this KV1? In some textbook, they denote the coefficient of velocity as KV1. So this suffix V denotes that it is related to the velocity, or it is nothing but our CV is equal to 0.985. Also, what is this KU1? U denotes that it is related to the wheel dia or the bucket dia. So the term associated with it that is speed ratio. So or in some textbook it would be shown by phi. So it is not our angle phi but the speed ratio phi. So here it is given by KU1. So you have to understand that it is speed ratio KU1, which is 0.45. So first thing that we can find out from this is V1, as we have done in the previous problem. V1 is equal to CV into root 2 GH. So from that we will get the value of V1. And we know that for a Pelton wheel we can write U is equal to U1 is equal to U2. So speed ratio is given. So to find out the velocity of the wheel, we have to multiply it by the speed ratio since it is given in the problem. So KU1 into root 2 GH, which will give you 38.85 meter per second. That is the velocity of the wheel. Now you already have another equation for finding out U, that is U is equal to pi dn by 60. So substituting that value, we can find out the value of d here because n is already given. From that capital D, that is the wheel diameter, will be 9.89 meters. From that you already know the ratio which is given in the problem. D by D is 1/6. So again you can find out small d, that is the diameter of the jet, just 0.165 meters. Now You are given the overall efficiency, that is eta O. Eta O is shaft power by water power, that is given by SP by WP. So since shaft power is already given, we have to find out this water power. Now how to find out this water power? Water power, the relation is rho g q h by 1000. So what is this q? Q is the total discharge. If q is the total discharge, we already have seen that the small q, which is the discharge of one jet. So discharge of one jet, we can find out area of the jet into velocity of the jet. Area of the jet, since we are assuming that the jet is of a circular cross section, it is pi by 4 d square into velocity of the jet is v1. Substituting the value, we will get the value of small q, but we do not know the value of capital Q. But as per our theory, we know that water power is rho g qh. Why divided by 1000? Because we have to get this in kilowatt, since this value is also in kilowatt. So substituting the value, the only unknown here is Q. So we already know eta O, which is 0.86. Substituting the value, we'll get the total discharge as 3.672 meter cube per second. Now we have to find the number of jet. That is our next question, next part of the question to be answered. So number of jet is nothing but capital Q by small q, or total discharge by discharge through one jet. We will get the value as 2 jets. So this is how you solve problems that do not require um, our velocity triangle. So basically, we can either solve the problems using the theory that we have studied, that is the shaft power and water power and all. And another kind of problem is those which are solved with the help of drawing velocity triangles. Hope you have understood both of this. So now we come to the next kind of turbine, which is the Francis turbine. So recall that Francis turbine is an invert flow reaction turbine which has radial discharged outlet. And in modern Francis turbine, water enters runner of the turbine in radial direction at outlet and then leaves at axial direction at the inlet of the runner. So because of this, we can say that it is a kind of mixed flow turbine. So before moving into the problem, we will see what are the important equations that has to be used in solving Francis turbine. Here again, Francis turbine, the an important thing to note here is that VW2 will be 0. That is, the world velocity at outlet will be 0 for a Francis turbine, because the discharge is radial at the outlet and the world velocity will be 0. So the work done per second, the formula will be slightly different in the case of Francis turbine. It will be rho Q into VW1 U1, and the work done per second per unit weight will be 1 by G into VW1 U1, and the hydraulic efficiency eta H will be VW1 U1 by GH. Now these are some of the important relations that we require for solving problems related to Francis turbine. So a Francis turbine with overall efficiency of 0.75 percentage is required to produce 148.25 kilowatt power, which is working at a head of 7.62 meters. The peripheral velocity is equal to 0.26 into root 2 gh, and the radial velocity of flow at inlet is 0.96 into root 2 gh. Wheel runs at 150 rpm. Hydraulic loss are 22% of the available energy. Assume radial discharge. Determine guide blade angle, wheel vane angle at inlet, diameter of wheel at inlet, and width of the wheel at inlet. So we note down the given things, and the peripheral velocity u1 is equal to 0.26 into root 2 gh. Substituting the value of h, we have it u1 as 3.179 meter per second. Similarly, vf1, that is flow velocity at inlet, again it is given radial flow velocity at inlet is 0.96 into root 2 gh. So directly from the problem we can get the value. and N is 150 RPM, and the hydraulic loss are 25% of the available energy. So what does that mean? Hydraulic losses are 22% of available energy means hydraulic efficiency of the turbine is indirectly given. So radial discharge at outlet is radial, and we can say that for an Francis turbine VW2 will be 0 and VF2 is equal to V2. Now hydraulic efficiency by definition it is total head at inlet minus hydraulic loss divided by head at inlet. So from that you are given 22% is hydraulic losses. So obviously the hydraulic efficiency will be 100 minus 22, which is 0.78. So 0.78 or 78% is the hydraulic efficiency, which is indirectly given in the problem. So we in last in previous session we have seen the equation for hydraulic efficiency, which is VW1 U1 by GH. So substituting the values, VW1 is equal to 0.78 into G into capital H, we already know, into U1. So U1 we have already got. So from that we will get the value of VW1 as 18.34 meter per second. Now again here also we have to draw the velocity triangle, which is shown here. So here, unlike a Pelton wheel, here the inlet we have a velocity triangle like this. It is not a straight line as in the case of Pelton wheel. Here we denote all the terms, that is V1, VR1 and VF1, U1 and VW1, and alpha and theta are the guide blade angle. Guide blade angle is alpha and the vane angle at inlet is theta. Now since VW2 is 0, the outlet side of the velocity triangle will resemble like this in the case of a Francis turbine. So this is the outlet side. This is here drawn like this: VR2, U2 and VF2. VW2 is 0, therefore we will not have any other components like in the inlet side. So first we are asked to find out the guide blade angle alpha. Alpha is in the inlet side or the inlet side of the velocity triangle. So we can see that tan alpha, we have to take the bigger triangle. So tan alpha is VF1 by VW1. Both quantities we know. From this we can easily find out alpha is tan inverse of 0.64, which is 32.619 degrees. Again, wheel vane angle at the inlet, that is theta, we have to find out theta. Again, take the smaller triangle theta. Theta is VF1 by, we can see, you have to see, refer this velocity triangle. So VF1 by VW1 minus U1, that is this much portion. VF1 by this much portion, that is VW1 minus U1. So we know all the terms. Substituting the values, again we can find out theta. Theta will be 37.74 degrees. Now the third part of the question is to find out the wheel diameter of the wheel at inlet D1. So since we have already got the value of U1, you know the expression U1 is equal to pi D1 n by 60. The same relation that we have used in the last problem for Pelton wheel. So from that you can easily find out the diameter D1, which is 0.4 meter. And again next part is to find out the inlet width of the wheel at inlet, that is we are denoting it by B1. For that to find out that, we are given the you know already that overall efficiency is shaft power by water power. Shaft power is given in the problem 148.25 kilowatt. Water power is rho g qh, converting that into kilowatt, rho g qh by 1000. So substituting that value, only unknown is q. Q is the only unknown. So substituting that value, q is equal to eta 0 is equal to 148.25 by 1000 into all these terms we substitute, and the overall efficiency is 0.75 or 75%. Substituting that value, we will get the value of q. So finally the value of q is or the discharge is 2.644 meter cube per second. Now how to relate discharge and the width of the wheel? You have the equation like this. This equation you have to study. Q is equal to pi d1 b1 into vf1. It is nothing but our Q is equal to AV. Discharge is equal to area into velocity. So here this is pi d1 b1 is the area, and Vf1 is the flow velocity. Substituting that value, we will get the answer of width b1 as 0.177 meter. Let us solve another problem. This is also similar to the one that we have just solved. You can read the question. All these things are given. That is, h is 60 meters head, and speed is given 700 rpm. Shaft power is given sp, that is 294.3 kilowatt. Overall efficiency, hydraulic efficiency, all are given. And the flow ratio is 0.2. So from that Vf1 we can find out 6.862. Here again the velocity triangle remains the same that we have just seen in the last problem. And breadth ratio is nothing but b1 by d1, which is 0.1. And you are given in the problem outer diameter d1 is 2 times the inner diameter. So if we can call outer diameter as d1 and inner diameter as d2, we can write d1 is equal to 2d2. Again, flow velocity Vf1 is equal to Vf2. That is, we are assuming there is no loss due to the impact. And the thickness of the vein, vein occupies about 5% of the circumferential area. So since the vein cover that much area, only the remaining is available for the actual area, actual flow. So actual area of flow will be 100 minus 5%, that is 0.95 into pi d1 b1, actual area of flow. So discharge is radial, that so we can write for a Francis turbine Vw2 is equal to 0 and Vf2 is equal to V2. And using the relation overall efficiency shaft power by water power, we can find out the water power, which is 350 kilowatt. Again, water power is rho g qh by 1000. So substituting the value, we will get the value of Q, which is 0.5952 meter cube per second. And again, substituting the actual area, we have just find out 0.95 pi d1 b1. So the discharge will be that much area into Vf1. So from that, substituting the value of substituting b1 in terms of d1, we know that b1 is 0.1 d1. It is given in the problem. So we get the only unknown is d1. So taking d1 is equal to square root of 0.5952 by 2.048, we will get a d1 as, that is the diameter of the wheel diameter as 0.54 meter. Again, breadth of the wheel we can easily find out 54 mm or 0.054 meter. Again, tangential speed of the runner at inlet, that is u1 is pi d1 n by 60. You can find out using this equation, and the value is approximately 20 meter per second. And again, hydraulic efficiency, from the relation of hydraulic efficiency, the only unknown is Vw1. So rearranging the terms and substituting the value, will get Vw1 as 27.66 meter per second. So here again in this problem, this velocity, drawing the velocity triangle is of very important. Marks will be awarded for this drawing this velocity triangle correctly. Now coming to solving, once we have got all these values, we have to find out all the things that are asked in the problem. First one is guide blade angle. Again, you have to see this triangle, bigger triangle. Similar way that we have solved in the last problem, Vf1 by Vw1. And similarly, the other angles, that is vane angles, theta and phi are called vane angles. Again, look at the triangles in inlet and outlet side, and substituting the values, we will easily find out the vane angles theta, and you will get the vane angles at outlet, that is phi. Okay, now the diameter at inlet and outlet we have already found out, d1 and d2. And the width of the inlet is also being found out, 54 mm. So this is how we solve these problems. Now we come to the last kind of turbine, which is the Kaplan turbine. So this is a figure showing the construction of Kaplan turbine. This we have already seen in our last video session. And recall that it is an axial flow reaction turbine, and vanes on the hub are adjustable. If the vanes are non-adjustable, it is called propeller turbine, and if the vanes are adjustable, it is called Kaplan turbine. And here it is mainly used for large quantity of water which are available at a low head. So let us look at some of the important relations for a Kaplan turbine. Here the discharge Q is given by pi by 4 d naught square minus dB square into Vf1. What is d naught and dB? It is given here. D naught is, or do is, outer diameter of the runner. dB is the diameter of the hub. So you already know what is a hub, what is a bose. These are the important parts of a Kaplan turbine. And Vf1 is obviously the velocity of flow at inlet. And some other relations, important relations for a Kaplan turbine is given here. So now we will look at some of the problems. A Kaplan turbine working at under a head of 20 meters develop 11772 kilowatt shaft power. Outer diameter of runner is 3.5 meters, and hub diameter is 1.75 meter. Guide blade angle at the extreme edge of the runner is 35 degree. Hydraulic and overall efficiency 88%, 84%. Velocity of whirl is 0 at outlet. Determine runner vane angles at inlet and outlet at the extreme edge of the runner, and the speed of the turbine. So these are the given things, that is H is given, shaft power is given, DO and DB is given, and the guide blade angle at the extreme edge of the runner. So you are given alpha is given. Alpha is the guide blade angle. And the hydraulic efficiency eta O, eta H and eta O are given. And whirl velocity VW2 is 0. This is VW2 is 0 for a Kaplan turbine. And you are asked to find out runner vane angles at inlet and outlet. So at inlet we call it by theta, and at outlet it is phi. So these are the things that is asked, and also speed of the turbine, that is n, is also asked. So what are the things to find out? Theta, phi and n. So here again the velocity triangle you have to draw, and you have to mark all these dimensions in velocity triangle as shown in this figure. Now using the relation, overall efficiency is always shaft power by water power. Water power is always rho g qh. So since it has to be expressed in kilowatt, it is rho g qh by 1000. So substituting those here, overall efficiency we already know 0.84 or 84%. Substituting the value, and h also we know, we will get the value of q. So the discharge q is 71.428 meter cube per second. And we have seen that the discharge for a Kaplan turbine is given by pi by 4 do square minus dB square into Vf1. So substituting the value, the only unknown here is Vf1. So Vf1 is 71.428 by 7.216, which is 9.9 meter per second. And from the inlet velocity triangle, we know that tan alpha is Vf1 by Vw1. That is the opposite side by the adjacent side. So from that tan alpha value is already given, we can find out the value of Vw1. Again using the hydraulic efficiency, eta h is Vw1 u1 by gh. Vw2 is obviously 0 for a Kaplan turbine, and from that you will get the value of u1. So once you have already got u1 and Vw1, so we now know the value of u1, we know the value of Vw1, and we have the value of Vf1. Now we are in a position to find out the value of theta. So again considering the inlet side, the smaller triangle, tan theta is Vf1 by this much distance. So Vf1 by Vw1 minus u1. Substituting the value, we will get the value of theta. And for a Kaplan turbine, u1 is equal to u2, and Vf1 is equal to Vf2. So we can similarly write tan phi. This angle tan phi is Vf2 by u2. So Vf2 is nothing but same as Vf1. So substituting these values, we will get phi as 39.035 degrees. And to find out the speed of the turbine, we have to find out n. So again our old equation u1 or u or u2 is equal to pi do by don by 60. From that we will get the value of n 66.63 rotations per minute. Now another problem, this also solved in the similar way. A Kaplan turbine which develops 24,647.6 kilowatt power. Average head is given, speed ratio, flow ratio, and the Bose diameter 0.35 times the diameter of the runner, and overall efficiency. You are asked to find out the diameter, speed, and the specific speed of the turbine. So you can find out all these quantities. That is U1 is speed ratio is given. So speed ratio into root 2 GH, you will get U1 as 55.32. Again, VF1, similar fashion, we can find out VF1 16.59. And you are given Bose diameter is 0.35 times the diameter of the runner or outer diameter. So dB is 0.35 times do. And overall efficiency is 90%. So overall efficiency shaft power by water power, substituting the value, you will get the value of Q 71.58 meter cube per second. So here again Q, discharge Q is pi by 4 do square minus dB square into VF1. So here substituting the value, the relation that dB is 0.35 times do, and VF1 we have already got it to be 16.59. Substituting all those values, we will get the value, only unknown is do. So we will get the value of diameter of the runner is 2.5 meter. So once diameter of the runner or do is got, you can find the diameter of the Bose 0.875 meters. And again speed of the turbine, the our equation pi dn by 60, substituting the value, n is 422.61 rotations per minute. And what is specific speed? The specific speed in mathematically it can be written as ns, n suffix s denoting the specific speed. Ns is equal to n into root of p by h raised to 5 by 4, where p is the shaft power in kilowatt. So you already know all these terms. Substituting the values, you will get the value of specific speed as 680.76 rotations per minute. So in other words, specific speed will be equal to the speed of the turbine when it is operating at a unit power and a unit head. So that is the definition for specific speed. So if you clearly observe this, we had solved two varieties of problem. One which was solved with the help of velocity triangle, and another one, that is this problem, with the help of a set of equations. So hope you have understood all these problems and how to solve the problems related to different kinds of turbine and how to draw the velocity triangle, etc.